Imagine someone making a truly wild claim decades ago, something about alien technology. Sounds totally sci-fi.
Right.
Now, what if, like, a key part of that story, something you could actually test scientifically, has been looked at, and, well, the results are pretty surprising?
That's exactly where we're headed today.
That's the territory for this deep dive.
We are indeed looking into the, let's say, long-debated story of Robert Lazar. He's the figure who, way back in 1989, claimed he worked on extraterrestrial spacecraft. Secret stuff.
Lazar, yeah. That name. It brings up Area 51, S4, Element 115. A lot of skepticism, too, right? For years, it feels like the talk has mostly been about him, his background. Can you believe him?
Exactly. But what if we just pivot, shift the focus away from the man, just for now, and look at one specific scientific detail he mentioned?
That's what we're doing today. Forget belief, forget conspiracy. We're zeroing in on the one single testable scientific claim Lazar made.
Which was?
That the alien craft he supposedly worked on pulsed a gravity B wave at a very specific frequency, 7.46 hertz.
7.46 hertz.
Okay. And this isn't just talk. We've got some really interesting research papers that have actually dug into this specific claim.
Using some advanced methods, too.
Ah.
Things like Quanti's Fourier harmonics and what they call the electrogravity-magnetic construct. Sounds heavy, I know.
It does sound heavy, but the implications, they're fascinating.
And what makes this deep dive different, maybe for you listening, is that we're not really asking you to believe anything.
No.
We're looking at how this one specific scientific statement holds up when you really analyze it. It's less about little green men, more about, well, fundamental physics, maybe, and potentially some aha moments about how things work.
Exactly. We'll try to unpack the physics, keep it accessible, avoid the super dense jargon, focus on the insights, and honestly, prepare for some unexpected turns here.
Okay, so let's start with that claim. 1989, Lazar says the craft pulses a gravitational wave, 7.46 hertz.
Right. 7.46. What's the big deal about that specific number?
Well, Lazar's idea, or the idea he presented, was that Earth itself naturally radiates a gravity B wave at that exact same frequency.
The Earth does. Naturally.
Yeah, that was the claim. And that the spacecraft's propulsion system worked by interacting with this Earth waves, counteracting it somehow to hover and fly.
Interesting. Okay, and the research we're looking at, what did it find about this 7.46 hertz? Is it real?
This is the crucial bit. The paper finds that this frequency, 7.46 hertz,
Right.
it seems to be a real fundamental property of the quantum vacuum, specifically Earth's quantum vacuum right at the surface.
Wait, hold on. A property of the quantum vacuum, like the background energy of space itself?
Kind of, yeah. Think of it like the fabric of space-time around Earth having this specific hum or frequency tied to our planet, right here at the surface. It's location-specific.
Wow. So it's a natural thing, part of Earth's environment. This is where it gets really interesting, doesn't it? What does that mean for Lazar saying it?
Well, this is what's truly fascinating, the scientific validation of this frequency. It doesn't actually need the rest of Lazar's story to be true.
What do you mean?
I mean, you don't need alien ships or Area 51 or S4 or Element 115 or Lazar's background check or conspiracies. None of that is required for this frequency to exist as a quantum vacuum property of Earth.
Okay, that's a big point. The physics stands alone.
It seems to, based on this analysis, the frequency could just be.
Which leads to the absolute core question, right? If this is a real natural property of Earth, how on earth did Lazar pick that specific number, 7.46, back in 1989?
Exactly.
Because mainstream science didn't know about this particular QV property then.
Not in this context, no. That's the enigma. How did he get it?
Right. Okay, so let's dig into the validation. How did the science actually confirm this?
So the research paper we're focusing on, it details how they mathematically derived a gravity B wave frequency and the number they got, 7.43 hertz.
7.43. Wow. And Lazar said 7.46. That is incredibly close.
This is remarkably close, yeah. Especially when you think, Lazar stated it to two significant figures, just two decimal places effectively.
Right, not like around 7 or 7.5. He said 7.46.
The odds of guessing that specific number randomly, statistically, it's extremely unlikely.
Okay, so it's probably not a guess. But what about other explanations? Could he have gotten it from somewhere else? The paper mentions the Schumann resonance, right? Some people connect it.
Ah, yes. Good point. The Schumann resonance. That's a known set of electromagnetic frequencies in Earth's atmosphere. The main one is about 7.83 hertz.
Okay, 7.83 versus 7.46. They sound kind of close.
They sound superficially close, which is why the comparison comes up. But the paper argues pretty strongly that connecting the two is, their words, absurd in the extreme.
Absurd in the extreme. Why so definitive? They give reasons.
They give 6 key reasons. First, Schumann is electromagnetic. It happens in the atmosphere. Lazar's claim is gravitational. Totally different physics, apples and oranges.
Okay, different forces. Makes sense.
Second, there's no known science, no engineering pathway to use the Schumann resonance for anti-gravity. You can't just, like, hum along with the atmosphere and lift a spaceship.
Right, that seems unlikely.
Third, the Schumann effect is trapped between the Earth's surface and the ionosphere. How would a craft coming from space rely on something bounded by the atmosphere?
Good point. What else?
Fourth, the numbers themselves, 7.83 hertz versus 7.46 hertz. If you look at them with the same precision Lazar used, they are statistically different values. They just aren't the same number.
So even the numbers don't really match up if you're being rigorous.
Exactly. Fifth, the percentage difference is about 4.7%. In engineering or physics, if your numbers are off by almost 5%, that's usually considered a significant difference. You'd probably say the hypothesis is wrong.
More than just experimental error.
Much more, typically. And finally, the paper basically says, look, these points together show there's no scientifically credible link between the Schumann resonance and Lazar's 7.46 hertz gravitational claim, period.
Wow, okay, so they really shut down that comparison. So this independent validation of Lazar's only scientifically testable claim. What's the real significance here?
It's potentially huge. Because this validation, based purely on the science presented in this paper, suggests that at least this one specific part of Lazar's story might actually be genuine.
And that challenges the usual arguments against him.
It directly challenges arguments based on, say, missing university records or perceived credibility issues. Because here you have a specific scientific data point that seems to check out decades later based on physics he couldn't have known then.
Okay, so we have this frequency, 7.43 derived, 7.46 claimed. Let's try to understand the science behind why this frequency might exist. The paper talks about limits in Einstein's general relativity. Why start there?
Well, general relativity, or GR, it's our best theory of gravity, incredibly successful. But it does run into trouble at really huge scales, like with dark energy, and also at the super tiny quantum scales. It doesn't quite mesh with quantum mechanics.
The very big and the very small.
Exactly. So physicists have been looking for alternative ways to think about gravity, or ways to connect it to quantum physics.
And one of these is the polarizable vacuum model, PV. What's the gist?
The PV model is sort of an optical way to look at gravity. Instead of thinking of gravity bending spacetime, imagine spacetime itself has a property like, well, like the refractive index of glass or water. They call it KPV.
Refractive index, like how light bends when it goes through a lens.
Precisely that idea. In the PV model, this refractive index of spacetime isn't constant. It changes depending on the energy density nearby, like near a planet or a star.
So more gravity means space-time is sort of thicker for light to travel through.
That's a decent analogy, yeah. And this variable refractive index makes light bend, mimicking gravity's effect as described by GR. But the key thing is the PV model links this to the quantum vacuum.
Okay, the quantum vacuum. Empty space isn't really empty, right? It's full of these virtual particles popping in and out.
That's the standard picture, yes.
Yeah.
Virtual particle pairs, VPPs. The PV model proposes that ordinary matter polarizes this vacuum. It influences these VPPs.
Polarizes, like a magnet affects iron filings.
Sort of, yeah. Matter creates gradients, changes in the energy density of the vacuum around it, and that's what changes the refractive index, KPV. It's a bit like how an electric charge polarizes the vacuum around it in quantum electrodynamics.
Okay, so matter influences the vacuum, changes its properties, and that's perceived as gravity. How does electrogravimagnetics, EGM, fit in? That sounds like unifying forces.
EGM is presented as a mathematical framework that tries to do just that, unify gravity and electromagnetism, using quantum mechanics and this quantum vacuum concept. It uses some pretty advanced math tools like Buckingham pi theory and dimensional analysis, basically to make sure the equations work out physically.
Right. Complex math. But what's the core idea in EGM?
At its heart, EGM sees mass not just as a lump, but as concentrated energy, a wave function density. And this mass energy is in equilibrium with the quantum vacuum energy around it.
Equilibrium. Like a balance.
Exactly. And it suggests that total QV energy associated with a stationary mass is given by EmC quarter. Einstein's equation comes right out of it. Plus, it proposes this energy isn't just static. It's distributed across frequencies in a specific way, a cubic frequency distribution.
Okay, cubic frequency. Got it. Now, physics has had this weird problem with the quantum vacuum potentially having infinite energy, right? Does EGM fix that?
That's a classic problem, yeah. The vacuum catastrophe.
Mm-hmm.
If you sum up all possible virtual particle energies, you get infinity. EGM gets around this by saying the QV energy spectrum around an object isn't infinite, it's finite, and its extent is governed by the object's own mass energy, MCR.
So the object itself sets the limit for the vacuum energy around it.
That's the idea. It links the vacuum energy directly to the finite rest mass of the object, resolving that infinite energy in a vanishing volume paradox.
That actually sounds more reasonable. Okay, so how do they get from EGM to deriving Lazar's frequency? It involves merging spectra and Quantis-Fourier harmonics.
Right. They combine the energy spectrum from EGM, related to the matter, with the spectrum of the empty vacuum, the zero-point field, or ZPF. They use the equivalence principle, the idea that gravity and acceleration are linked as a guide, and then apply this technique called quantized Fourier harmonics.
Fourier analysis. That's like breaking down sound into notes, right?
Exactly. It's breaking down a complex wave or field into its fundamental frequency components. Quantized just means these frequencies come in discrete steps or modes, not a smooth continuum.
Okay, breaking down Earth's gravity field into its harmonic frequencies, how does that lead to 7.43 hertzes?
So they use this derived PV frequency spectrum, and it simplifies nicely near Earth's surface because that KPV value, the refractive index, is very close to 1. They then use something called a unit harmonic operator.
Unit harmonic operator. Okay, another term. What's its job?
Think of it as the mathematical tool that lets them isolate and analyze these quantized frequency modes of the gravitational field. Their analysis found something remarkable.
What was that?
They found that almost all, like 99.9% of Earth's gravitational acceleration is contained within the first 415 of these harmonic modes.
Only the first 415 out of how many?
Potentially infinite, theoretically. But the first 415 do almost all the work. They call this number N Lazar. N Lazar equals 415.
And Lazar equals 415. So what happens when you plug that number into their equation?
So when they sum the contributions of just those first 415 modes, using their KV frequency spectrum math, they calculate a frequency. They call it Toll Lazar, the theoretical Lazar frequency, and it comes out at 7.43 hertz.
7.43 hertz, derived from summing the first 415 gravitational harmonics of Earth, and Lazar claims 7.46 hertz. The paper points out that's a 99.64% match.
An incredibly tight match, yeah. Derived from first principles physics, essentially.
That is stunningly close. It really makes you wonder how Lazar could have possibly known that number.
It really does, which leads to the next logical questions the paper addresses. Why stop at 415? Why L Lazar equals 415? And couldn't you use, say, 1,000 modes for an even better anti-gravity effect?
Right. If it's about counteracting gravity, why not use more harmonics?
These become engineering questions. The researchers introduced two concepts here: spectral power flow, SPF, and the spectral power amplification factor, SPF. Basically measures of the energy cost.
Ah, so it's about power consumption, how much energy it takes.
Exactly. It's a trade-off. Their analysis suggests that N Lazar equals 415 is kind of the sweet spot, the optimal engineering solution for hovering. It gives you a very high degree of similarity to the gravitational effect you want to counteract without requiring an absolutely insane amount of power amplification.
So using more harmonics, say 500 or 1,000, it would work better, but cost way too much energy.
That's the finding. You hit diminishing returns. Going significantly beyond 415 modes gives you only a tiny bit more anti-gravity advantage, but the SPF, the power amplification needed, skyrockets. It becomes incredibly inefficient.
So 415 is the practical, sensible engineering choice if you're building something based on this principle.
Yeah, so the analysis strongly suggests, yes, the most bang for your buck, energy-wise.
Fascinating. The paper also briefly mentions, this is really out there, an anti-gravitational atom. Maybe element 115, connecting it to the proton.
Yeah, that's more speculative, venturing into potential mechanisms. The idea is if such a thing existed as stable isotope of element 115 with anti-gravitational properties, as Lazar claimed, maybe its unique behavior comes from how it interacts with the quantum vacuum differently than normal matter.
Differently how?
They float the idea of a quantum vacuum phase difference relative to the proton. Since protons make up most normal matter's gravitational interaction, maybe this exotic atom is somehow out of phase with the vacuum compared to protons. It's highly theoretical, of course.
Really pushing the boundaries there. Okay, final piece, artificial intelligence. How did AI get involved in evaluating Lazar's story?
Right. So given how extraordinary the whole story is, and now having this one piece of validated data, the researchers used AI, specifically Bayesian probability and Monte Carlo simulations, to try and assess the overall likelihood of Lazar's narrative being true. Crucially, based only on the strength of the 7.46 hertz claim validation.
Bayesian probability. Can you give us the simple version?
Sure, Bayes' theorem is basically a way to update your beliefs based on new evidence. You start with a prior belief, how likely you thought the story was before the evidence. Then you factor in how likely the evidence, the 7.46 hertz match, is if the story is true versus how likely it is if the story is false. It recalculates the probability.
Okay, so you tell the AI how skeptical you are initially.
Yes, they ran simulations with different starting points, like assuming only a 1% chance Lazar's story was true initially, highly skeptical, or maybe 20%, or even 50-50.
And what did the AI spit out after crunching the numbers? Considering the 7.43, 7.46 match?
Even starting from very skeptical priors, the validation of the frequency had a huge impact.
Yeah.
The AI ran millions of simulations, 2.4 million, I think it was, and its conclusion was an overall probability of the story being true landing somewhere around 82.1%.
82%. That's a massive jump from 1% or even 20%.
It's a significant shift, yes. The AI analysis basically highlights that this 7.46 hertz claim and its apparent validation is the linchpin. It's what makes the narrative statistically compelling, despite its otherwise extraordinary nature.
But the AI also stressed this probability depends entirely on that frequency validation holding up, right?
Absolutely critical point. The 82% isn't proof of aliens. It's a statistical assessment saying if this frequency validation is correct and robust, then it dramatically increases the odds that the source of that information, Lazar, had genuine knowledge. Without that validated frequency, the probability would likely stay very low.
Okay, so let's wrap this up. What's the main thing you think people should take away from this deep dive into Lazar's 7.46 hertz claim?
I think the biggest takeaway is that a claim once easily dismissed as sci-fi nonsense made by a controversial figure actually contains a specific testable scientific component. And that component seems to align remarkably well with an independently derived fundamental property of Earth's quantum vacuum.
It's pretty mind-bending. Lazar somehow stated a principle related to quantum physics and Earth's gravity field years before the theory explaining it was developed, all hinging on that one number, 7.46 hertz.
Precisely. And for you listening, maybe this offers a different angle on a familiar story. It shifts the conversation, at least partly, from do you believe to what does the scientific analysis show? It might just change how you think about the boundaries of known physics.
It really does make you wonder. If this one key detail checks out mathematically, what does that imply about how we should evaluate other parts of Lazar's story, or other extraordinary claims in general? Are there potential breakthroughs hidden in plain sight, just outside the mainstream? Does validating this one piece make the whole wilder picture suddenly seem less impossible?
Those are exactly the kinds of provocative questions this research raises. It doesn't give easy answers, but it definitely pushes the boundaries. And if your curiosity is piqued, definitely check out the papers themselves. Look into the quantum vacuum, PV, EGM. There's a lot more to explore there.